Click logs are great training data until position bias poisons the labels. Here's how to debias clicks with inverse propensity weighting and train a ranker in LightGBM. This is the setup you'll be able to run after this, which debiases click logs with inverse propensity weighting and re-ranks results for a query. I'm Professor Pi, teaching search and IR with simple Python. Search teams collect click logs because clicks are cheap signals of relevance. The problem is simple to state. Users click more on the first results. That extra attention makes clicks look like relevance, even when the lower results are actually better. Counterfactual learning to rank from click logs fixes that. It treats clicks as biased observations and asks how to recover the hidden relevance behind them. Success looks like a re-ranker that learns from existing logs and pushes truly relevant items up, not just the ones that got eyeballs. Intuitively, inverse propensity weighting rescales clicks by how likely a position is to be seen. Think of a click as a noisy vote. A top result vote counts less because the top gets more votes just from exposure. A bottom result vote counts more because it was harder to get. That simple idea lets us turn exposure-skewed clicks into usable labels for supervised ranking. The weakness is that propensities must be estimated. If they are wrong, the correction swings the wrong way. But with reasonable estimates, you get better training targets than raw click counts. We will build a tiny, self-contained example you can run locally. It simulates a click log, where higher ranks get more attention. Then we debias those clicks using inverse propensity weighting. Finally, we train a LightGBMRanker with and without the weights and compare the re-rank on a small held-out query. You will see how underexposed but informative clicks influence the model once we re-weight them, and why that matters for real systems. Now we start by simulating clicks. Now, we simulate a tiny click log. This example generates a tiny click log where higher ranks get more attention, so clicks reflect position bias. The list rels holds hidden relevance grades, while prop encodes position propensities that dampen or amplify click chances by rank. Inside the loop, base maps relevance to an intrinsic clickability, and multiplying by prop simulates how exposure inflates top results and suppresses lower ones. We tally clicks and compute CTR per position by dividing by the number of impressions. Increasing N reduces sampling noise, while adjusting prop makes bias more or less severe. The printed CTR gap shows how raw clicks favor top ranks, regardless of true relevance. Next, we correct the observed click rates. This snippet corrects the observed CTRs using inverse propensity weighting, so each click is scaled by its chance of being seen. The list IPS divides each position CTR by its propensity from the earlier simulation. The variables AdgeTop and AdgeBottom capture the debiased rates for the first and last positions, which become more comparable than the raw CTRs. This helps transform attention-skewed supervision into a closer proxy for relevance. If propensities are underestimated, the correction will be too strong. If overestimated, it will be too weak. The printed values illustrate how IPW raises lower rank estimates while tempering top rank inflation. Now we train a baseline ranker on the raw biased clicks. This code fits a LightGBM LGBM ranker on toy features using raw click labels as targets. The list X holds simple numeric features for 2 queries, while Y encodes click-derived labels that are likely position biased. The list G specifies query groups, so the ranker learns within query ordering. The model is created with N estimators and learning rate to control capacity and speed, and fit is called with group to enable pairwise ranking loss. After training, predict scores the first query's candidates, and top selects the highest scoring document. Increasing N estimators generally increases fit quality, but can overfit. The printed top document shows the ranker's current pick under biased supervision. Next, we train the same model, but feed it inverse propensity weights. This example reweights training with inverse propensity weights, so LightGBM learns from Debias signals. The list pause assigns a position to each training row, and W turns those positions into weights by taking 1 over the propensity from earlier. The IPW model is the same LGBMRanker class, but fit receives sample weight, which upweights underexposed ranks, and downweights highly exposed ones. The skew ratio compares total weight at the bottom versus the top, showing how much more influence tail positions have now. Raising propensities narrows this ratio. Lowering them strengthens debiasing. The printed skew confirms the training signal meaningfully shifts toward lower ranks. Finally, we score a held-out query with the debiased model. This snippet applies the debiased LightGBM LGBMRanker to score a small held-out set. The list XQ contains new candidate features for one query, and IPW model predict produces scores aligned with the counterfactually reweighted training. The variable top identifies the highest scoring document index, while max SQ shows its score for visibility. Because training emphasized low propensity positions, the model favors features supported by less exposed but informative clicks. Increasing N underscore estimators in training could sharpen separations, while a lower learning rate would typically require more trees for similar accuracy. The printed top document and score demonstrate a tiny complete re-rank using debiased learning. In a real project, this maps directly. Replace the simulated propensities with logged exposure models or an eye tracking estimate. Replace toy features with your production features. Train at scale with grouped batches and validate with holdout queries. The same IPW idea scales from this tiny demo to millions of impressions. Recap what it is. Counterfactual learning to rank recovers relevance from biased clicks by rescaling signals with inverse propensity weights. When to use it? When you must learn from logged clicks instead of human labels or interleaving, and exposure is uneven. One caveat: propensity estimates matter. Bad propensities produce bad debiasing. Wrap punch. Next, tune the propensity model or replace the simple one with a learned exposure model and measure how re-rank quality changes. That single change often yields big practical gains. If short, practical IR helps, subscribe and watch the IR videos.